Hi everyone, thanks for coming along. Last chance, if this isn't the talk you intended to come to, going to do a talk about CMake. I really hope you're not expecting anything really startling, because this is a talk from a CMake beginner, as will become apparent. But these are things that I've picked up that I found useful, excuse me, and I just want to pass that on and hope that it's useful to somebody else. So this is me in various places, and I'm not hard to find. But please get in touch if you've got any comments after the fact. But yeah, speak up with questions if there's anything that's not clear on the way through. Anybody that recognises me at all knows I'm not a C++ developer. I'm a .NET guy. And so written a couple of books about .NET, but that's not what we're going to talk about. But it is relevant, which will become also apparent in a minute. So is this talk for you? I wonder if you're one of these three eggs. There's a guy on the left who looks a little bit anxious about something, in this case, CMake, or grumpy about it if people mention it, because, you know, it's difficult. Or you're in the middle, just sarcastic. If somebody says CMake, no, I'm not doing that. So I was all three of these when it became apparent that I needed to do some stuff with CMake. So if you're any of these eggs, then hopefully I'll have something that can help. My background, although I've been doing .NET development for decades, I originally came from a C and C++ developer role, and Microsoft Visual Studio has been a constant companion, really, throughout my career, but doing C++ stuff particularly long ago in sort of C++ 98 kind of environment. But the setting up Visual Studio hasn't changed that much in all that time. And doing things like figuring out where they include what, you know, how to include custom include paths, link to static libraries, set the version of the standard library that you want to use. All of these things are usually done in Visual Studio property pages. Now, IDEs vary. Some are easier, some are harder. If you're already familiar with command line tools like Make, particularly on Linux-based systems, then the CMake stuff will probably be less unfamiliar to you. But if you come, as I did, from a Windows, predominantly Windows environment, using dialog boxes like this to configure your system. Now, this was the property pages in Visual Studio. They're very, very comprehensive. You can twiddle all sorts of switches, and you can even import property pages as kind of as text, so that you can put them under version control, so that everybody can share the same settings, but it's properly arcane stuff. You know, working with custom property pages in Visual Studio is really not for the faint of heart. Even less for the faint of heart than using CMake is, I think. So I wanted to get away from this. About a year or so ago, I was doing a C++ talk, and again, this was a C++ talk as me as not a C++ programmer, but it became apparent that doing all of the config using CMake was just going to be easier, because I wanted a little packed environment that I could put into version control, and it would work for Visual Studio, it would work for GCC tools on Mingu, I could use Windows Subsystem for Linux if I wanted or needed to, and the config would just work. And that is the magic of CMake. That's the headline thing, right, of why you want to learn CMake, is because you've got this little packaged environment for simple stuff. It genuinely is quite simple. And you don't have to worry about twiddling switches in property pages. So that was my motivation, really, for getting to grips, at least a little bit, with CMake. So the plan today is I want to show some simple examples and do a couple of little demos, introduce some core important concepts. The idea is not really to make you into CMake experts. Sorry, but it isn't. What I hope to get across at the end of the day is or what I want you to be able to take away, is to be able that you can recognize the general structure of a CMake project, or in the small CMake file, but slightly larger than that because you can have more than one. And we'll talk a bit about that. But it also that might help you get started from scratch, rather than trying to figure out from first principles what a CMake file is. And okay, quick show of hands, anybody never seen a CMake configuration file ever? One person. So are you familiar with, when I say CMake, do you know what I mean? Have you run a CMake command line to build somebody else's software? Okay. You might be the ideal person in the audience. What I want to do is this is one of the CMake files that I use to build the code that backs this talk. I'm not going to be showing an awful lot of code, to be honest. But what I want to do is to stop this from, when you open a file that looks like this, from turning into gobbledygook. And if you don't see the difference between those two slides, then this talk really, I hope, will be useful. Because when I first saw CMake, I suppose I want to step back a bit, is although Microsoft Visual Studio has been a companion of mine for a long time, a few years ago discovered C-Line from the JetBrains people, and I love it. So I've been using their tools for years in .NET world, and I've been using Rider as an IDE for C# development for a long time. And I wanted to go into C-Line and see how that worked, because it fits into my personal environment a bit better than Visual Studio does. And it's got support for different compilers in a way that Visual Studio makes that difficult. So C-Line has CMake support built in from first principles. And whilst it can work with Visual Studio project files, it's one of those things that the IDE kind of turns its nose up and goes, I don't know, all right, I'll open that file and set up a project for you, but you really should be doing this in CMake. And that's kind of why I wanted to figure it out, because I wanted to fit into C-Line's natural environment, because it makes my life easier working in that tool. So I wanted to get a simple example up and running. And so this slide, I think this is, classically the smallest C++ program. There are bits of controversy in that source, but don't worry about it. It's a 4-line C++ program. I'm not really going to talk about the code. I want to build it. The simplest CMake lists.txt file to make an executable program that runs from that source. So CMake lists is the configuration for your build system. So CMake itself isn't really a build system, although I don't get precious about that sort of things, but it is there to create a build system for you. And this is the minimum you need. Just from the top, CMake minimum required, that's the version of CMake that is needed, because CMake has been around for quite a long time. It's gone under quite a lot of revision in that time, with new features added, existing features changed, and so on. So you need to tell CMake what version to expect, what actual version of the environment you're using. So it is that CMake minimum required line is needed in every CMake file. And then we're going to create a project, and project here is just a label. We're just going to call the project hello. And that is just a name to hang other things off in the CMake config. It doesn't really create anything. But what does create something is the add executable. And that's doing the heavy lifting here. So add executable names a target, where the target in this case is called world. And that, when we build this, we're going to end up with an executable program called world. Because I'm doing it on Windows, it's going to be called world.exe. And it's built from a source file called main.cpp, which is that thing on the left. And that's all you need to get started with that. So it's a single line, a single source, simple C++ program. But in principle, it shows some quite important concepts. So in order to create that executable program, these are the steps that you need to take. Firstly, we take the CMake list text and build the build configuration. So it's when people talk about, has anybody ever heard the expression that CMake is a make maker? And in a sense it is. It can be used to make files to be built using make, which has, obviously a long history in programming. But what that top command, the -big B bin, does is it's going to create a folder called bin and put all of the configuration needed to build your source into an executable target, in this case, in there. You only need to run that command when you change the configuration itself, the CMake list.txt. Before I forget, it is now possible, allegedly, for the CMake config to be called something other than CMake list.txt, which even I think is a pretty ugly name for a make configuration, but it's not recommended. CMake basically expects the file to be called CMake list.txt, and if you're working on Linux or any Unix-like environment, then it's also case sensitive. Just remember that. The next command you need to do is to actually run the build. So CMake --build bin is going to use the configuration it generated in that bin directory to produce the executable. And this performs an incremental build on any changes to the source files, and those are detected by CMake or the build system, depending. And then we can run it. So, right. Hello. So the question is, does it create the configuration in that bin folder, or is it using one that's already there? Hopefully, this little demo will make that clear, but it creates the configuration and puts it in that bin folder.
Thank you.
So I have got a little canned environment where I've got my CMake list.txt and my main.cpp. Is that clear enough to everybody here? Okay. So if I show you the CMake list.txt, it's just those same 3 lines and the same C++ program. And actually the code in the slide is just including these files, so I know that it's the same. So the 3 steps I've got, thing to note is there is only those 2 files in that folder. So I'm going to first create the bin folder using CMake -b bin. And that has detected that I've got Visual Studio automatically, because it's looked in some well-known places, and it's creating me a build based on Visual Studio project files. So it's now created that bin folder, which has got basically the scaffolding that you would expect for a Visual Studio project. There's a solution file, a VCX proj file, which is just the project file, which refers to that one source file that we've got. And this is the build configuration that CMake has just generated for us, having auto-detected my toolkit. It's not built anything yet. There are no executables in there. We've not built the source code. We have created the configuration for the build. So the next thing to do is CMake --build bin. And what this will do is use the configuration in that bin folder and run the tools to build it. So again, it's auto-detected that I'm using MS-build, the Visual Studio toolkit. It's gone through, checking the build system, building the rule set, found main CPP, found there's a VCX proj file that it can use to build using the build tools, and it's generated world.exe in bin debug, also under that bin directory. So you can change these defaults where the outputs go, but this is the simplest case. So now I should have, under bin, in debug, something called world.exe that I can run. You can applaud now, okay? So it's all that's the simplest example I could come up with. But if I delete that folder, there, and I just run up the Windows subsystem for Linux. So this, if you're not familiar with that, it's basically, in my case, it's an Ubuntu distribution running on my Windows box. But it has its own environment and its own tools. And in this case, I've deleted the bin directory. I'm going to recreate it with that -b bin. And this time, it's found that I've got GNU tools. It's auto-detected the GNU tools in my Linux distribution. And it's created the build system for the GNU GCC compiler in bin. And in this case, it's created me a make file. And this is where the term makefile maker comes from. CMake has just created me a make file, just a bog standard make file, that I can now use to build the code for the current target. So if I run the build, CMake -- build bin, it compiles using GCC, and this time in bin, it's created my world executable. It hasn't put it in a debug folder because the defaults are different for GCC. But if I run it, I get the same output. That's from the same configuration file for 2 different platforms with no changes. And that's quite profound. That's what CMake is giving me, is a platform-independent way to configure my code for compilation and compile it with the toolkit that is native to the system that I'm on. So let's come back out of that. Because I can also, under Windows, it previously auto-detected that I got Visual Studio installed. So just by default, when I ran CMake -big B, it auto-detected the Visual Studio stuff and it generated me a Visual Studio solution pack. I can change that because I've got a Mingu with the GCC tools on my Windows box as well. And I can ask CMake to use that instead. CMake -b bin, and I can say -g, which is generator, and I'm going to use something called Ninja. And as you can see, this is now, I'm back in Windows. I've come out of Windows Subsystem for Linux. This is now auto-detected by telling it about Ninja, that I've got GCC 14, and it's created me. Well, it hasn't created me a make file. That's a bit odd. This time, it's created me a build Ninja file. I'm going to talk a little bit about Ninja in a moment. But now when I run the build itself, it's now created me a world.exe using GCC tools. So not only have I got cross-platform configuration for my build, I've got cross-tool as well on the same platform. And that's pretty powerful stuff. So I could tell CMake from the same configuration file to use GCC tools, to use Clang, to use the Greenhills compiler if I had it, to use Visual Studio if I want to, whatever toolkit I've got, I can provide support for CMake to generate the build for that, and then anybody can build from it. So if I'm working in a team, and part of the team are working on a Linux platform and part of them are working on a Windows platform, the same configuration can be used by everybody, rather than exporting property pages from Visual Studio or whatever, or generating make files, or however all that stuff fits together. So the simple stuff, I hope you'll agree, is pretty simple, but also pretty powerful, even in the most simple case. And I'm sure it doesn't take much imagination, I hope, to see that that power scales out to real projects. So Ninja. I said earlier on that CMake isn't really a build system. And some CMake enthusiasts get really upset if you call it a build system because it's much more than that, but it's also a bit less than that. Ninja really is just a build system. So if you know what Make does, then you understand at a high level what Ninja does. Ninja is kind of a replacement for Make. And instead of Make files, it uses the ninja.config that you kind of saw in passing a moment ago. Like Make, Ninja is independent of the toolchain. So it's independent of GCC or Visual Studio, but I can use Ninja to build those targets if I want to. And it's fast. So it's, in fact, fast is its principal reason for being. Make, which historically has been used as the kind of the lingua franca build system, particularly for C and C++, but also, I mean, it goes back to building Fortran and Forth and all sorts of other kinds of things. Make has been around a long time. But it works on a set of rules, and it builds based on the declarations you put in your Make file. Make infers the rules from it as it goes, and then builds the targets by their dependencies within the file. Ninja doesn't have rules. You have to tell it what to do, step by step. It doesn't do any rule generation or rule understanding. You basically say, build me main.cpp, and it goes, okay, I'll build main.cpp, regardless of anything else. Whether main.cpp depends on something else, well, that's not quite true. We'll come to that. But it basically, you give it a list of files to compile, and it goes through one by one and compiles them really, really quickly, because that's what it does. It's not a rule system, it's a build system. Make is kind of slow because it tries to be both. But the configuration is by non-humans only. So if you're familiar with Make files, actually I should probably have left a Make file there. Let's create one again. So this is what a Make file looks like. We've got a bunch of stuff that's been generated by CMake on our behalf, including a load of implicit rules and some dummy targets, phony targets they're called, which handle things like dependencies which aren't there yet, which might be in the future, or being able to build targets that don't generate something like a clean target. And thanks for it. You know, it's quite big, but it's human readable. And if you understand Makefile, then, you know, you can get to grips with that. If I go to my bin directory, which has my build.ninja in it, if I vi that, we've got this is the important bit, the build. This is not human configurable. It's not intended to be. In fact, on some platforms, the build ninja file is a binary that you can't edit by hand. And that's deliberate, right? What Ninja is supposed to be configured by other tools, specifically CMake. Doesn't have to be, but CMake's good at it. And did I mention it's fast? It's fast. It really is fast. It's much, much quicker than Make, even in the small single source file case. But Ninja is just a build tool. So I could also say, if you remember, I added a -G Ninja, so telling CMake what generator to use. There's a whole list of generators for various compilers, including Mingu makefiles, Unix makefiles. You can create generators for lots of different platforms. If you're interested, go and investigate. It's quite fun, actually, building for different things and getting different tools lined up. Yeah, it's just my geekiness. Anyway, so CMake, headline positives. We've got a common builder configuration that's independent of my toolkit. I can use the -G generator on the command line to switch between toolkits if necessary. And it's a consistent process for everybody on the team. Everybody knows how to build it. They might be using slightly different command line switches for their own environment, or they might not. But the point is that we abstract away the complexity of the project by using CMake configuration. And this means the build process can be version controlled. So if you are familiar with Make, historically, then Make is just a text file, then it would go under version control. Things in Windows are slightly different. As talked about the property pages in Visual Studio, that's for C++ programmers on Windows. Visual Studio property pages was kind of the thing. There is something called NMake, which is the Visual Studio version of Make, and there's, it's a different dialect to ordinary Make, and it does some slightly different things. And it just, if you try to mix Make and NMake, then you're in for a world of pain. But with CMake, we can coalesce all of that complexity into a single CMake list.txt, giving us multi-platform and multi-target builds. And the build process is part of the code in the same way that a make file would be, but it's much smaller and more compact. And it's therefore CI server friendly. So if you're doing a continuous integration build on a shared server somewhere, your CMake, even if that shared build is running on a different platform, it doesn't matter, because we can, as long as the tools are there and CMake knows how to use them, then we can build our system in a different environment. So the build agent environment can differ to the one that I use on my workstation. Question here? So the question is, can I mix and match back-end tools from the command line? Yes, you can. I don't know how. So I don't know, for example, how to make Ninja build a Visual Studio project, because I don't need to do that. Oh, I haven't needed to do that. But I know that it's possible. So yes, Ninja. So Ninja is independent of the toolchain, and Visual Studio does come with its own Ninja built in, and the Mingu download comes with Ninja built in. But it might just be which one you use that's top of your path. I really don't know. I know it's possible. If you find out, let me know. So, okay. Hopefully, I'm getting across the idea that CMake is really good, and that it's quite, it's simpler than the alternatives, particularly the historical alternatives. But shouldn't we just use Make? Because Make does all this stuff already. Well, Make has its own issues. If you've ever had to do anything sophisticated with Make, you'll probably sympathize. Multi-file projects are a bit more difficult because you're setting up dependencies between them. Compilation time is an issue, particularly for C++. I mean, obviously, C++ compilers have got better over the years. But back when I was using Visual C++ 96, maybe, C++ took a long time to compile, especially if it had templates in it. It was a nightmare. Dependency management also feeds back onto compile time and link time stuff. So Make allows you to do the dependency management in a reasonable way and the incremental builds in a reasonable way. But all of the compile time stuff, it's difficult, yes. So the basic question is, are there aspects of things that CMake supports that only specific generators allow? So the particular example was program compilation database for introspection with Clang. Don't know what that is. Sorry, not a C++ programmer, as previously explained. So yes, I think is the answer to that. The longer answer, I don't know, not tried, not played with it. There are definitely things that are back-end tool specific. So by this, I don't mean the build generator, I mean the compiler. So if Clang has got support for some specific thing, then that's probably only going to be floated up through it would have to be Ninja or Make, probably. I don't know, Visual Studio has Clang support, and so it might be that MS Build allows you to, I don't know. I'm not sure. That's kind of way off my radar. Any others before I move on? Okay. So Make comparison. With the proliferation of platforms, tools, configurations, environments, all of the other stuff, Make environments get out of hand real quick. If you've ever seen a large project that was based on Make files, the build system can be a little hard to understand. And then, on top of all that, we've got different dialects, so NMake, Make, others. All of the dependency management, the rule sets that are either, they might be implicit, and so you're trying to figure out what Make might be thinking, as well as the explicit dependencies and rules. Auto tools for Linux and Unix-based environments was partly around helping to manage this, particularly the proliferation of different platforms and targets, so that auto tools configured would generate you a build configuration in a very similar way that CMake did, but its cross-platform support was frankly a bit poor. It was mostly just Linux, frankly, really, for all intents and purposes. And then pre-compiled headers and things like that, which support for that really is platform-specific and proprietary, although that's got better over the years. Make was starting to show its age. Well, I mean, it's fair. It's 60 years old, maybe. So, CMake. It's cross-platform build tooling, primarily for C++ projects. It doesn't have to be C++. It's not specific to C++. It is really the de facto standard format for configuring builds now. That just is the truth. Because it supports everything, it does everything you need. And it's a meta build. It's a make file maker for many platforms. But it is more than that, because it is giving you the flexibility of switching out your toolchain, switching out the generator, probably combining switching those out for other things. So that the end goal of all this that CMake wants to support is a very small, in the simple cases, configuration file, a CMake lists.txt, that can work for all the developers on your team, regardless of their toolchain or platform. That's its goal, to take all of the variation away so that you can have a single configuration that works for everyone, or at least nearly everyone. Jason?
I just like the one thing that confirmed that it is only the Ninja generator with works with modules.
So Jason Turner's just looked up the support for modules is specific to Ninja and Visual Studio, but yeah, for the recording. Thanks, Jason. So CMake is good, and it's very powerful, but with great power comes an enormous amount of documentation. So if anybody has ever gone to the CMake documentation site, particularly with the only thing you've ever known about CMake is the instruction said run CMake -- build in this folder, which was me, and you look at the documentation and go, wow, that's a lot of documentation. And it's extremely comprehensive documentation, but you've really got to know what you're looking for in order to make sense of it. So the thing that I really wanted to show you was that simple examples really are simple. The simple stuff just works. So moving slightly on from the most simple C++ program is let's change things up a little bit. Here, instead of just writing a string literal out, we're going to include a file. And the file is going to contain the string that gets written to the output. And this is dependency inference. So if we change the header file, what gets recompiled? So remember the simple CMake list.txt file that we had. This is almost the same, except that the name of the project and the name of the target have changed. And obviously the source code has changed. Let me see if I can do a demo. Yeah. So here's my CMake lists. Project, as I say, that's just a label. Here I'm creating an executable called custom message, but again from my main.cpp, which is including my message.h. So I'm going to scaffold a build, just because, oh, what have I broken? Nothing, just forgot to clean up. I scaffolded a build using Ninja, using the GCC tools, and I'll build it and run it. So that says hello CMake. Now, I should be able to do make a change to, whoops. A change to the .h file, remember. And I don't need to run the build scaffold, the big B command again, but I do need to rebuild the code. And that, hopefully, has detected that I changed the header file without it being mentioned in the configuration. So CMake has inferred that dependency, and it does this, so all of the mainstream compilers support forcing the tool to output the dependencies for all of your source files. And CMake makes use of that to figure out what the dependencies need to be. Actually, it passes it off to Ninja in this case, but Visual Studio supports it natively, so it avoids that extra loop round. But the point being that I don't need to name all my header files. If I add a header file, even recompiling the code is enough. I don't need to rescaffold the build. I just need to recompile. And that's the nub of an incremental build. You rebuild for changes to source. And if I rebuild again, it's not going to do anything. It says no work to do because I haven't changed anything. So incremental builds out of the box. That's not really difficult in Make to arrange to do that, but you have a lot of extra manual steps to do, including particularly the dependency database that you need to get whichever compiler you're using to spit out so that you can feed it back into the build. Don't need to do it with CMake, it does it for you. Other things not in the box. I might have a non-standard system include. In this case, I'm using the magic enum, which apparently from after this weekend I don't need anymore. Is that right? With reflection? What magic enum does, it basically allows you to use introspect on enum classes. It is the headline. Don't worry about that. The point being, I'm using some third-party include. I need to tell CMake where to find it. I might have it in a well-known place. I'm using system include syntax because it's not a local include, and that's just housekeeping. Not that it doesn't really matter. It's just I tell CMake where my include directories are in the configuration. Now, what I'm introducing here is something that needs all the developers on a team need to have it in the same place. But you can make variables for this kind of thing. I'm not going to go into that, but you can arrange so that CMake can find your well-known includes in different places, depending on what platform you're working on. Obviously, that introduces complexity to the config, but it's complexity you would have had to do with makefiles too. But the point here is that in my CMake file, I've got my executable called cards, which is the target. And I'm telling CMake that for that target, here is the path to the include directories. And there can be more than one path. There's a list of paths that I can add in. And that can be relative to the wherever. In this case, because I'm using a relative path, that's relative to the location of the CMake list.txt file that I'm currently compiling or currently scaffolding. I think that's all I need to say about that. A similar idea if I've got a static library that I want to include in my build. So here I've got target include directories that are bringing in the small fast media library. So the include directories, I point off to the includes. I've got target link directories, which are going to go off. That's the location that contains the static libraries for whatever platform I'm on. And then my target link libraries, there will be a separate target called bounds with the source files for it in the same way we've seen, just for shortness of the slide. Here I'm saying when I link my target called bounds, I also want to link against effectively the import directories for these, which are dynamic libraries by default in SFML. And hopefully, yeah, this is the same thing. So here I've got my add executable called bounce up here, and putting in the include directories, the link directories for those, and linking against the SFML libraries at the end. And it's all clean. So if I do, for this one, I do need a Ninja build because I've only downloaded SFML for the GCC toolkit. So I'll build against it. And then I've just built a simple Windows app. So that depends on the actual dynamic libraries for SFML being somewhere on my path, just because they are not copied as part of the build. Now you can arrange for CMake to figure out what your dynamic dependencies are with some caveats and create a package into your output directory. Not going to touch that at all today because it's way off the scale of complexity in CMake world, frankly. But it is possible to do that. Or you could just write a script that does the copy. Hello. So the question is, what's the best way to manage different build types on the linked libraries? So debug mode versus release mode, static library versus dynamic libraries, a bit like this. So you're a slide ahead of me. So it does allow me to specify with a really simple syntax. When I'm doing a debug build, I want to link these libraries that have got -d at the end, that's the debug convention for SFML particularly. For an optimized build, so an optimized build is basically anything that's not a debug build. So in CMake language, you only have two variants. It's got debug mode and non-debug mode. But so the question is, when I'm doing a debug versus a release build, the target that is being linked together to be an executable, I've got a release version and a debug version. Is that what you mean? Yeah. And so when I build, I can't remember the command line syntax for this. You can, by default, when I type CMake ---- build, that builds me debug, and that will put it into one folder. I can specify I can basically configure a different folder to take a release mode build, and it will have all of the built targets in there. Talk to me afterwards, I'll show you, because it's about the invocation of CMake that distinguishes between debug and release. And you can arrange for those two things to output to different folders. But it's the CMake lists configuration that tells it what to link, not what to build. It's a kind of a fine distinction. It's a really good question. I'll try and, yeah, I've got to move on. Speak to me after. There is a better way to do some of this, where I can set variables within CMake. So this is going to build a standalone executable. Couple of changes here. I'm creating a variable for the main location of my SFML libraries and includes, so that I can use that base path in the rest of my config. I'm also here saying, rather than specifically specifying that, so which libraries to which specific libraries to link against, what I'm saying here is I'm telling CMake to go and find a package called SFML. And this works because SFML has built-in CMake support. So the SFML developers have created the CMake build files for their own stuff, exported enough, including this name SFML, so that my CMake file can find it. And then find package will go off and look in some well-known places, which I am helping it along with by setting this CMake prefix path. And I'm in the find package, I'm telling it which components to build in. In this case, components called graphics, window, system, and those are SFML names. They're not CMake names. But what this also allows me to do is that when I'm linking in the final line on this configuration, the target link libraries, I'm specifying the package name that comes from SFML rather than the specific libraries. So that gives me a little bit of flexibility in the configuration, but it also makes it easier for me to share that configuration with other people. This is the most basic example on this, because using CMake variables is really key to making your CMake config, particularly if it's relatively complex, being able to share that with other developers on a team. A couple of other things to note is I can pull in third-party dependencies by artifact. So in this case, I'm asking for Google test, and I'm using a facility in CMake called fetch content. It's kind of an external facility to see. It's not part of CMake core's functionality, but it is a, by extension, an include thing that you can pull in with, from including the fetch content package, and then I'm declaring what it is that I want as Google test is the name of the thing that I'm after, and this is where to go and get it. In this case, I'm downloading from a URL a specifically version zip package. And then I'm making it available so that all the targets that are part of my own configuration, in this case, something called gtests, can depend on by name called Google test. And what CMake will do here is, if it hasn't already cached this package, it will go off, download it, and unpack it into its cached area, so that I can link again. I can use this include paths, which come, again, this depends on Google test having some basic CMake support built into it. But there is enough smarts in that configuration to know that it goes to there for the include paths and where to find the libraries to link against, so that I can just say, I'm going to link against gtest main, so that I don't have to write my own main in my unit test package. So this abstracts you away from manually downloading it yourself, although obviously you can and refer to that, which is important under continuous integration server situation, for example. Rather than a built package, I might do it by Git reference. So here, it's the same basic idea, but I'm doing it for catch 2, where include fetch content declare for catch 2. This is now a Git repository on GitHub with a tag. And that what CMake will do under this circumstance is clone that tag to its cached area so that I can then use it in the rest of my program. By extension then, for example, in a CI build, I might want to manually clone it to a local place because my CI build server might not have access to the internet. It's quite common to firewall off build servers. So you can have your own clone that the build server does have access to and build against that instead. Realistically speaking, we haven't got time to go through the next slides. So I'm going to zoom across it. What I do want to talk about is a little bit about physical versus logical shape. I'm going to do this really, really quickly, but here I can have a CMake lists file for a project that's got, in this case, is a main project, it's got a test project, it's got a static library that it links against internally and also makes available to other programs, and an executable that pulls those things together. I can have a single CMake lists file at the top level of the project that knows where all these things are, what the targets are to build, and I can specify dependencies between them. And it's not terribly complicated in this case. For a large project, obviously a single CMake lists file is going to be enormous. So you can split them up in the same way, if you're familiar at all with Make. You can have nested Make files. The difference is that the CMake, having nested CMake files, it just works rather than you having to do anything else. Whereas nested Make would, anybody that's ever used nested Make files will have had a proper eyebrow twitchy moment where of not being able to figure out why something hasn't been pulled into a build. CMake, you just include the path to the CMake file as a directory. And so in the middle one, under heating triggers about halfway down, I'm telling it to include directories, and I can say specify whether to include it before or after the current one that's being built. And it all just works. And it really does. And then at the end, you can have your final target built. But also it means that I can, for example, I might want to build my tests independently of everything else. I might be changing the tests only, not want to build all of the infrastructure that's being tested because that hasn't changed. I just want to build the tests. Because it's got its own CMake lists file, I don't need to remember what the target's called. I can just go to the directory and build it. So quick word about tooling. CMake comes with a GUI, and I can't recommend that you use it unless you already know CMake in a lot more depth than I do. Visual Studio and C-Line both have pretty good CMake support. C-Line in particular, the support for CMake, it is properly integrated into the IDE. In Visual Studio, it feels like a bit of a bolt-on, which is because it is. C-Line support for CMake files is outstanding. I started off the talk saying I love JetBrains tools, and I still do. So that's me. All done. Thank you very much. Any more questions?